Related rates. I really like related rates. They're one of my favorite sections. It's not easy, but by the same token, take your time, be careful. It's not too terribly difficult. The idea is, how does the rate of change of one thing correspond to the rate of change of something else? This first example is essentially trying to to demonstrate how you're going to be taking your derivatives in order to apply them. We are going to be taking the derivatives with respect to time, as time changes. So that's what we're dealing with, as time changes. It's a rate. How this changes over time, how does data change over time? How do the two things relate to each other? I will say that I give you in here, and I do give you on the test, certain formulas. AP does as well. AP does not expect you to remember the volume of a cone, nor do they expect you to have memorized the volume of a sphere, the surface area of a sphere. I know those three they definitely give you if you need them for the test. They will actually, in the test question, they'll give you that, those, just like I have here. Certain ones they do expect you to know the volume of a cube, volume of a box of any shape. You should be able to do that on your own. Cylinders, I'm not sure on cylinders or not. But I know cones and spheres, they give you cones and spheres. Okay, so volume of a cone, 1/3 pi r squared h. How is dV dt related to dH dt? In other words, the rate of change of volume relates to the rate of change of height if r is a constant. In other words, take the derivative of the volume of a cone, leaving r as a constant value. So if r is a constant, that doesn't change. Just take the derivatives with respect to the other variables. So the derivative of v is dV dt. The derivative of 1/3 pi r squared h is 1/3 pi r squared dH dt. Because if r is a constant, if the radius does not change, but only the height is changing, that is my relationship between the two. Okay. How is dV dt related to dr dt? If h is a constant, if h doesn't change. Okay. So the derivative of volume with respect to time, dV dt, is equal to 1/3 pi r squared h. If h is a constant, it doesn't change, but the derivative of r squared, bring down the 2, so I have 2/3 pi r h dr dt. That's if h is constant, if the height does not change, but the radius does. So very difficult to imagine those first two actually happening. The radius of the cone stays the same, but the height of the cone changes. The radius changes, but the height does not. And it doesn't make any sense. So the last one, how is dV dt related to dr dt and dH dt if neither of the variables is a constant? Well, this is similar to taking the derivative implicitly. Derivative of volume is dV dt. The derivative of 1/3 pi r squared h, how many variables do I have in there? I have two variables. When I take the derivative of one term with two variables, I have to do it twice, one for r, one for h. We know what the derivative for r is. We already did that. 2/3 pi r h dr dt. And the derivative of the volume, or with the height, with respect to height, but r is a constant, we already did that one as well, equals, plus 1/3 pi r squared dH dt. The rate of change of the volume is equal to 2/3 pi r h rate of change of the radius plus 1/3 pi r squared, the rate of change of the height. How fast does the height and radius changing affect the change in volume? Kind of makes sense. Think about, rather than a cone, an inverted cone. You've got a conveyor belt dumping sand, and the pile is growing. Well, what shape is the pile? The pile's in the shape of a cone. I'm adding sand at a constant rate because the conveyor belt's moving at a constant rate. I'm adding sand at a constant rate. How fast is the radius and the height changing accordingly? I can relate how one thing changes to how something else changes. That's the whole idea of today's lesson. One thing changes, how does that affect something else? It's very difficult, very, very, very difficult to solve for 3 changes at a time. 2 at a time you can do. So often you're going to have to change so you get just 2 variables, the ones that you're talking about changing, and eliminate the 3rd one or 4th one some other way depending upon what you're talking about. Okay, steps for solving related rate problems. Learn it, know it, live it. Get these down. Okay, so step number 1, identify the problem, identify what you know and what you're seeking. 2, develop a mathematical model of the problem. Draw and label a picture. I cannot emphasize enough, draw and label pictures of what's going on. It will help you tremendously. Okay, it really, really makes a difference. Identify the constants and identify the variables. Some things will change, some things won't. Some things are constant. They have a numerical value that does not change. Write an equation relating the variable whose rate of change you seek with the variable whose rate of change you know. Often the equations will be given to you, sometimes they won't. And sometimes you have to do that, you have to change them. For example, volume of a cone. It is very difficult to do the RDT and the HDT both. You will only generally be dealing with one or the other, which means you'll have to figure out the ratio and setup and replace R with something H or H with something R to get it down to 2 variables. V equals something in the terms of either the radius or the height. And we'll work on how to do that. Differentiate both sides of the equation implicitly with respect to time. Substitute values for inequalities that depend on time, and interpret your solution. In other words, solve the problem. Take the derivative, then plug in the values. Don't plug in values beforehand. Take the derivative first. Very common mistake. Well, I know what this is. I know that is. I'm going to plug the numbers in now, and then take the derivative. Well, if you plug the numbers in, what do you have? You no longer have variables. You have constants. And you need to take the derivative while they're variables, and then evaluate the derivative. Evaluate that function that you created with the derivative, the equation you created. Okay. Questions? All right, let's get to it. I said there we go. A ladder, ooh, I love ladder problems. Very common problems, ladders. Ladders are very common problems. Okay. A ladder, 20 feet long, leans against a vertical building. The bottom of the ladder slides away from the building at a rate of 2 feet per second. How fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? What is the rate of change of the angle between the ladder and the ground? So I have 2 questions I need to answer. I need to answer how fast is the ladder sliding down the wall? How fast is the angle between the ground and the ladder changing? 2 different problems. We will attack one at a time. Okay, first thing, it's a vertical building, which means that I have a nice little right angle here. Oh my God, that makes it so much easier, does it not? Okay. You want to label your triangle. X, Y, and Z for your 3 dimensions. The information given to me. Z equals 20 feet. Okay. If the bottom of the ladder slides away from the building at a rate of 2 feet per second, dx dt is 2 feet per second. That's what that tells me. It's sliding away at 2 feet per second. Ooh, that's a rate. Amount per time. 2 feet per second, dx dt. Okay. How fast is the ladder sliding? Oh, so the question it's asking me for part 1 is, what is dy dt? When the ladder is 12 feet above the ground, when y equals 12. So that's just for the first question. That's what I have. Now, what equation do you think best describes this situation here that I could use to describe this situation? Pythagorean theorem. It is. You got a right triangle. It's either going to be right triangle trig or it's going to be the Pythagorean theorem. You only use trigonometry when you're talking about angles. I am not yet talking about any angles. I am just, at this point, talking about the sides. If all I'm talking about is the sides, the Pythagorean theorem is your best friend. So that means I'm going to use x squared plus y squared is equal to z squared. So I'm going to take that. I have some information. I have 2 of the sides, right? I have 2 of the sides. One of them is 20. One of them is 12, and its y is 12. And so I need to figure out the third one. Okay, there's a couple ways to look at this. Pythagorean theorem will set it up, but it's also a Pythagorean triple. It's not. Yeah, 3, 4, 5 times 4. So this one would be what, 16? 12, 16, 20. Is that the one that works out? Yeah. 3 times 4, 5 times 4, 4 times 4. So this would be 16. Or you could just plug in the 2 numbers and figure it out from there. Either way would work fine with me. Okay. But you should know some of your Pythagorean triples. Okay. So 16, I have x, y, and z. Great. But I need to deal with rates. Take the derivative of that with respect to time. Doing it implicitly with respect to time. So the derivative of x squared would be 2x dx dt. That's how fast dx dt is the rate of change of x, of it sliding away, how fast it's sliding away. The derivative of y squared would be 2y dy dt. And the derivative of z squared would be 2z dz dt. Each variable with respect to time. Now, I know some of those values, and I'm looking for some of those values. What am I looking for? I'm looking for dy dt. What do I know? I know dx dt, and I know all the rest of them too. So I just plug things in. Okay, so 2x, x is 16, so 2 times 16 times dx dt, which is 2 feet per second, plus 2 times y is 12. And dy dt is what we're looking for, is equal to 2 times 20 times, what is dz dt? It's 0. This is not a collapsing ladder. The ladder is one solid 20-foot ladder. It is not a collapsing ladder. We're not dealing with Chevy Chase hanging the lights on the house with the ladder slides down on it. That's a whole different problem. Okay, so dz dt is 0 because the ladder itself is not changing length. That adds a whole other dimension to the problem that you don't want to deal with. Solve that for dy dt. So dy dt would be equal to negative 2 times 16 times 2 over 2 times 12. Which would reduce down to what? 8/3?
Yes.
8/3. dy dt equals negative 8/3 feet per second. Why is it negative? Because it's going down. It should make sense. Going up, it's sliding up, it's positive. It's sliding down, it's negative. Remember your negatives and positives. You have to have that relationship. So this kind of makes sense. If it wasn't at 12 feet, but it was at a different place, the rate would be different. We've all seen ladders fall. You've seen things fall. They don't fall at a constant rate. This is a snapshot in time. At the instant that it's 12 feet down, how fast is it falling? If I'm talking at 6 feet down, it's going to be at a different rate. Okay, but you can only do it at a particular instant. But I can relate how fast it's moving out to how fast it's falling down. That's what we just did. Okay. Questions so far? Okay, now the second question we had asked to us is, what is the rate of change of the angle between? So I need to figure out theta. Hard. Really isn't that difficult. So I've got to come up with an equation that describes theta in terms of the other sides. I like to use given information, not found information. So I'm going to want to use x and z. Because x is a constant, z is a constant, it doesn't move, so dz dt is 0. dx dt is our given information, dy dt is our found information. So what trig ratio works with the hypotenuse and the side adjacent? Cosine. The cosine of theta is equal to x over z. That's my relationship. Okay, that's my relationship that I have. Right? Opposite is adjacent over hypotenuse. Cosine is adjacent over hypotenuse. Okay. Take the derivative with respect to time. Okay, the derivative of the cosine of theta is what? Negative sine theta d theta dt, because I'm taking it with respect to time. Equals the derivative of x over z with respect to x. Well, that's x times 1 over z, right? X over z is x times 1 over z. So x times a constant, the derivative of x times a constant is that constant. So that would be 1 over z dx dt. And the derivative of z dz dt is irrelevant, is it not? Because what is dz dt? It's 0. So the derivative for z is irrelevant. So I actually don't have to worry about it.
It won't always be relevant.
It won't always. If it is, you would still have to take the derivative, but it depends. If z is changing as well, then yes, you have to include that as well. If it's not, then you don't have to worry about it. It's constant, it's not changing. Questions? Okay, so why am I not including dz dt here? Because z is a constant, dz dt is 0. It's not changing. I could take the derivative. It would be negative x over z squared dz dt, and dz dt is 0, so it doesn't matter. Plug in the values I know and figure out the ones I don't know. It's actually not as hard as it looks. Okay. What is the sine of theta? This is the one that's probably got you tripped up the most. But I have a right triangle. The sine is the ratio of two sides. In this case, the sine of theta would be 12 over 20. The side opposite over the hypotenuse. So I have negative 12 over 20 d theta dt is equal to 1 over z, 1 over 20 times dx dt, which is 2. Multiply both sides by negative 12 over 20. Or sorry, negative 20 over 12, my bad. Times negative 20 over 12. Those cancel. D theta dt is equal to, well, here the 20s cancel. And the 2 and the 12 reduce. Negative 1/6. And this would be in radians per second.
And that's just that. That value is what exactly?
Okay.
That's the change.
That's how fast the angle is collapsing. So the ladder's going, how fast it's collapsing at that moment. So the angle is shrinking. I like the ladder problems because you can ask all kinds of questions. How fast is the area formed by the ladder and the wall of the ground changing? That's actually not as hard as it sounds because the area of a right triangle is basically the two legs, 1/2 times leg 1 times leg 2, and you know dy dt and dx dt, you can figure out dA dt. Hardest part's figuring out what equations to use. Okay. Questions on this? Very common type of problem. Ladder problems are used all the time. All the time.
Why couldn't we use like the thing that we were taught last year, like doing like sine 90 over 20 like equals sine x over 12?
You mean the law of sines?
Yeah.
Yeah, but what's the sine of 90?
But I didn't get the same answers.
Then you did something wrong.
Well,
So you can't. So
You can use the law of sines, but when you have right triangles, don't use law of sines and cosines. And frankly, you will not need law of sines or cosines for just about anything we do in here. It's all right, almost everything we do in this class, right triangle.
cool.
Yeah, and you should know your right triangle ratios. Okay. Example number 3. A water tank has the shape of an inverted right circular cone of altitude 12 feet and base radius of 6 feet. If the water is being pumped into the tank at 10 cubic feet per minute, approximate the rate of change of the water level at the instant the water level is 3 feet deep. Okay, so I'm giving you the equation that you need. But I have a problem. Let's write down the information that's given to us. 10 cubic feet per minute. What is 10 cubic feet per minute? dV dt. Because 10 cubic feet is what? Volume over time, dV dt. So dV dt is equal to 10. You want to put units, you can put units, cubic feet per minute. And it's being pumped in, so that is plus, not minus, not being pumped out. Very important whether it's going in or out. Okay. What am I being asked? Approximate the rate of change of the water level at the instant the water is changing. Water level would be what? It would be dH dt. That's what it's asking me. H is how deep it is. It's asking me for dHdt. That's what I'm trying to find. When at the time H is 3. At time H is 3, what is dHdt? So when it's 3 feet deep, how fast is it rising at that particular moment? You can't do a general term. The only thing that's constant as far as the rates go is dVdt. Generally, it's pumping at a certain rate, right? You turn on the faucet, water comes out unless you adjust it. Water comes out at a fairly constant rate. How fast something is filling depends upon the shape of the object you're filling, how fast the height is going up or down. So think about this cone. The water's going in. I've got a hose I've turned on, or spigot I've turned on that's filling the tank up. The water is going in at a constant rate, but the height is not changing at a constant rate, is it? The bottom, it's going to be filling faster, so the height's going to be rising faster at the beginning than at the end. You can't, dHdt changes, even if the dVdt is constant throughout the whole thing, dHdt will change depending upon how deep it is. That's why I'm saying at 3 feet deep, what is it right there? What's going on at that moment? That's all we do is at that moment. We can find a relationship between them. Okay. I have a problem though. How many variables do I have in my equation for volume? I've got 3. I've got V, R, and H. All 3 of those technically are variables. dVdt, I got that. dHdt, I'm looking for. R, R's a problem. I don't know the RDT. I can't find the RDT and the dHdt at the same time. So I need to eliminate the radius. However, that's actually much easier said than done, or done than said. Easier done than said. Because what do I have here? This is a constant ratio. And the height and the radius always form that also constant ratio. What kind of 2 triangles do I have here? I have what? Right triangles, but they are also what? Similar triangles, which means the ratio to height and radius is always the same every time, which means the radius over the height is always a 6:12 ratio. Okay. And I can solve this and figure out that, the radius, or sorry, the height is always twice the radius. Cross multiply, solve for H, and the height is always twice as big as the radius. Always. No matter how deep it is, it's always twice. Which means that I can take this, or actually I want to do it the other way around. I want to eliminate, I want R in terms of H. So that means R is H over 2. Radius is half the height. So I can take this and replace it with this. So my new volume, 1/3 pi H over 2 squared times H. The radius is always half the height. Always. No matter what it is, it's always half the height. Because it is that constant ratio, I can do that and eliminate one of my variables. Simplify before you take the derivative. So H over 2 squared is H squared over 4, right? Bring the 4 forward, so my volume is 1/12 pi H cubed. Right, because I get H squared times H gives me H cubed. The 4 squared gives me, or sorry, the 2 squared gives me 4 in the denominator, bring it up. I have that. 2 variables. The 2 variables I want to relate, volume and height. Those are the 2 things I'm looking for. I have dVdt, I'm looking for dHdt. I need to have just volume and height, no radius. I eliminated my radius successfully. Now I take my derivatives. So, dVdt is equal to, bring down the 3, 3 over 12 becomes 1 over 4, pi h squared dh dt. Seen problems like this be part of the AP test. So far, we have gotten 3, usually like 3 out of 4 points. In the last other crap too, we can round it out to 9. Plug in the values, you know. 10 equals 1/4 pi 3 squared dH dt, and solve for dH dt. dH dt equals, let's see, so that's 9/4. So multiply that by 4/9. So 40 over 9 pi. Yeah. And this would be feet per minute. And it makes sense that it's positive because if it's filling up, the height would be rising after all.
The old switcheroo.
Questions so far? No. You get it down to one equation relating the two things that have the two things you want to relate to each other. Take the derivative with respect to time, plug in the values, find the thing you're looking for. It's kind of what you need to do. Any questions on this? The Borg have just assimilated species number 4782, and their cube is expanding at the rate of 100 cubic meters per second. What is the rate of change of the surface area of their ship? Borg, one of the best sci-fi villains ever. If you don't know, you should look them up and watch just a couple of clips.
We are
the Borg. Lower your shields and surrender your ships. We will add your biological and technological distinctiveness to our own. Your culture will adapt to service us. Resistance is futile.
Thanks.
So, what am I dealing with here? I'm given, well, what am I given here? I'm given, that's what? That's change in volume, right? Cubic meters is volume. So this is dV dt equals 100 cubic meters per second. What am I looking for? Change in surface area. I'm looking for ds dt. And I actually I'm missing something. I just realized I'm missing something on this. Because you have to give it at a particular time, at a particular moment.
Yeah.
I forgot I did this last year. So, surface of the ship when the side is 25 meters long. There. The extra information you need. Now, here's my issue on this one. I'm dealing with volume and I'm dealing with surface area. Is there a formula, an equation, if you will, that relates to volume of a cube to the surface area of a cube. Not one that directly does. Could we, if we were intelligent people, and we are intelligent people in this classroom, no matter what some of you might think of yourselves, you are intelligent people. Could we, if we worked at it, come up with a formula that does that? You could. You could. It's not pretty. I've done it. It's not pretty by any stretch of the imagination. We don't want to do that. Here's what we want to do. If we think about this as a two-step problem, and we deal with the volume of a cube and the surface area of a cube, two of them both related to the side length of the cube. I can take this one and solve for dx dt, and I can use this one here, use dx dt from this equation to solve for ds dt on that one. Use this one to find one rate that I can use in here to find the second rate that I need.
Why would the first rate not give you any input?
Well, I have dv/dt and I have ds dt. I need to somehow relate the two. Like I said, if I really wanted to, I can solve this for x in terms of s, plug that in, or s in terms of x, plug it in here, get x equals something s. Got square roots, and then I got to cube those square roots, and ooh, like I said, it's not pretty.
Yeah.
And then I've got to take the derivative of that. You don't want to do that. No, you don't want to do that. That's what the ugly part is. It's not so much getting the formula, it's taking the derivative of that formula and then having to do it. Because you still got to figure out what the surface area is. But if I do this one here, I take dv/dt is equal to 3x squared dx dt. And I can solve that for dx dt. I have the information to solve this for dx dt. And then I take this equation, and I get ds dt equals 12x dx dt, and I plug in the dx dt that I found here into that one to find ds dt. That's what I have to do. It's the easy way to do it. Trust me. I've done it the hard way just to see if you can do it the hard way. You don't want to do it the hard way. Okay, so dv/dt, this is 100, equals 3 times 25 squared dx dt. So, I need to calculate for this one.
He's trying to solve for dx dt. So it'd be 12 one more, that's not.
So you end up getting 4 over 75 is equal to dx dt.
Yeah.
I love fraction buttons on my calculator.
Is that 25?
75. 4 over 75. Because you just plug in 100 over what you got with on the other side 1875. 100 over 1875 reduces. It reduces for me.
Oh, I know.
So now I can solve for ds dt. I'm going to change colors just to make it a little easier. So ds dt is equal to 12 times 25 times 4 over 75. 12 times 5, I get 16. So ds dt is equal to 16 square meters per second. So like I said, if you really, really want to, you can try to relate volume and surface area in one equation. It's not that hard to set up the equation. The derivative, on the other hand, is difficult. The derivatives here were very easy to do. The derivative of x cubed, really easy. The derivative of 6x squared, really easy. Much easier to do it this way from that standpoint, rather than try to rearrange to set up one equation with two variables. Sometimes you can use two equations and get where you need to go to in a little more circuitous route. It still works. Questions? Okay, your turn. No. Okay, so let's do this. So Frosty's spherical head is decreasing a rate of 3 cubic inches per minute. So that means dV dt is equal to negative 3 cubic inches per minute. How fast is the diameter shrinking? Dd dt equals what? When d equals 10 and when d equals 8. Okay, that's the information given. You're given a formula. The volume is 4/3 pi r cubed. However, are we talking radius or are we talking diameter? You can do it in the terms of radius and make adjustments on your answer, or you can do what you really should do, rewrite that in the terms of, instead of terms of r, in terms of d, in terms of the diameter. What is the relationship between the two? The radius is equal to the diameter divided by 2. So my volume is equal to 4/3 pi d over 2 cubed. My volume is equal to 1/6, right? Yeah, 1/6 pi d cubed. Um, 1/2 cubed is 1/8. 1/8 times 4/3 is reduces to 1/6.
Oh, that's not right.
Right? Now 1/2 cubed is 1/8. 1/8 times 4/3. The 4 and the 8 reduce, you get 1/6. Take the derivative. Okay, dV dt is equal to, bring down the 3 over 6, 1/2 pi d squared dd dt. And then you plug in your values. You need to do it twice. Once for 10. Okay, so 100, that's 50. Right? And then you do it for d equals 10. Negative 3 equals 1/2 pi 8 squared dd dt. 8 squared is 64. Half of 64 is 32.
Oh, you weren't there. Oh, yeah,
Okay. So, at what time is it shrinking faster? At what time is the diameter changing fastest?
Oh, negative 3 over 55.
At 8. Because if the numerators are the same It's the opposite of the size of the comparison of the size of the diameters or denominators. 3/8 is larger than 3/4, smaller than 3/4. So the smaller the diameter, the larger the fraction. So it's actually shrinking faster. And it makes sense. You have more surface area, you have more volume when it's larger. The amount of volume you lose off the outside of a circle, a larger circle, is going to make a smaller change than one on the inner circle if you're removing the same amount of stuff. It makes sense. So the smaller it gets, so it starts shrinking slowly. The smaller it gets, the faster it gets. The diameter goes down. And that makes sense.
No.
Poor Frosty. You need to get a hot house. Questions? Okay.